Good afternoon, everybody. Welcome to the next year of the Science of SLAC lecture series. Thank you all for coming. Our first speaker this year is Aaron Rudman, professor here at SLAC. He's going to be talking to us about the Large Synoptic Survey Telescope and all the awesome science we'll be doing with that. So Aaron started his career over just down south from here at Caltech as a PhD student before moving to the University of Chicago, where he's working on the CDF experiments and also looking at the antimatter asymmetry in the kaon system. And around 1998, Aaron came to join us here at SLAC, working on the Babar experiment, again looking at the difference between matter and antimatter experimentally. So after about 20 years of trying to understand why the universe is made of matter and not antimatter, Aaron switched his research focus to looking at cosmology and trying to understand why there's so little matter in the universe in the first place, and trying to understand something about the nature of the dark energy and the dark matter that we think makes up the majority of the content of our universe today. And to that end, he's been heavily involved in the Dark Energy Survey and the Large Synoptic Survey Telescope that we're involved in here at KIPAC. And it's the LSST, the Large Synoptic Survey Telescope, that Aaron's going to be telling us about today.
Okay. Thanks, Debbie. Can people hear me? Yes. So the title for the talk is A Deep Look for Dark Energy. And as we go, I'll try to explain what that means. So this is the engineering drawing of the Large Synoptic Survey Telescope. This is the instrument that we have begun to build and that we're very excited about. And it's what I'll tell you today. Now, the mantra, in some sense, of the LSST is, let's see, go back one, is wide. Wide because we will take images with our telescope of the entire sky. This is a map of the sky, just like a map of the globe, but this is a map of the whole sky, north, south, equator. And the colors are meant to show how much of the sky we'll be able to observe with the LSST. As you can see, it's virtually everything that you can see from a mountaintop in Chile. It's fast. It's fast because we will take these images rapidly enough to be able to observe every part of the sky, every part of the sky visible from a mountaintop in Chile at that time of the year in 3 to 4 nights. So that every point on the sky will be observed many, many times over 10 years. And to do that, you have to be fast. And it will also be deep. And and the other one. The colored region is observed a little less frequently. This is the galaxy. This is how the galaxy shows up. The pole is a touch less interesting and a little bit harder to get to. And this region is the ecliptic. So this is where solar system objects will lie. So that's why we go above the equator here, but not everywhere. But we look at the galaxy, but because it's such a dense region, we don't look at it quite the same.
And the gray area?
That is the northern hemisphere. Can't see it at all. Okay, the last part of the mantra is deep. The telescope is big enough, the field of view is wide enough, we take so many images that we can observe galaxies that are extremely dim, and literally the technical word for that in the astronomical community is that's deep observing. You're seeing things, very dim things far away. This is actually a simulated image. This is what the images from the LSST should look like. There's false color in this image, so it's a combination of, first of all, a combination of many, many individual images, and then a combination of images taken with different optical filters. And they're put together with false color. This is similar to what it would look like if you could see this with your naked eye. Of course, to see it with your naked eye, you would have to have a very big eye. So the technical definition of deep is in a funny astronomical unit called magnitudes. It's a logarithmic unit that is actually designed to match what how the ancient Greeks classified stars. So it actually is a good object lesson in being careful about defining your units, because if you do it, you might be stuck with them for 2,500 years. So these images go to about 26.5 magnitude. And the bigger the number, the deeper you go, the dimmer the object. So with your naked eye, you can see about 4. Maybe here, if you look over the valley, maybe it's 3.5. But in a dark spot, it could be 5. So that's the mantra of LSST: wide, fast, and deep. Let me tell you a little bit more. So let me move now to talk about first some of the scientific goals, especially our aim to learn more about dark energy. So a little bit about what dark energy is and how LSST will be capable of learning more. I'll talk a little bit about the instrument, the telescope, and especially the camera, which we'll be building here at SLAC. And then lastly, talk about some of the other science that we'll be able to do with the LSST. But first, just one retrospective. To talk about dark energy, it's worth saying something about the expansion of the universe. And that was discovered around 100 years ago, with much of the key work done by Edwin Hubble with this telescope. This is the 100-inch telescope at Mount Wilson in the hills or the mountains above Los Angeles. And in some ways, things haven't changed. This telescope is very recognizably similar to the LSST in certain ways. But in certain ways, of course, we've gone far past it. In particular, the instruments that they're working on here, have in the end photographic film. And of course, today we digitize everything. We have electronic detectors, and in our case, we have this spectacular camera that LSST will use. So Hubble discovered that the universe was expanding. And in the time since then, if you go back, say, 20 years, we thought there were one of 3 possibilities for the expansion of the universe. And actually, up until about 20 years ago, we did not know which one was correct. What are the 3 possibilities? Possibility 1, that the universe would expand forever. And that's what would happen if the density of matter in the universe was too low. And because the expansion is potentially modified by the gravitational interaction of the universe on itself, if there wasn't that much matter in the universe, if the density was low, then what would happen is that the universe would just continue to expand forever. That's possibility 1. Possibility 2 was if the density of matter was too high, above some critical amount, the universe would expand, and eventually it would stop expanding, and then it would contract, ending in the corollary to the Big Bang, sometimes called for fun, the Big Crunch. Perhaps another Big Bang. That's what would happen if the density was too high. And of course, there's a case right in the middle, the Goldilocks situation. If the density of matter was just right, the universe would still continue to expand, but as it expanded, it would do so more and more slowly and sort of asymptotically continue to kind of zero expansion, but never quite getting there. So those are the 3 possibilities, and it all depended on how much matter was in the universe. So we discovered around not quite 20 years ago that actually all 3 of those possible futures, all 3 of those histories for expansion were wrong. And the reality was somewhat different. So I'll just tell you just a little bit about that. The key in doing that was finding a certain class of objects, a certain class of supernova, exploding stars, for which we could measure both their velocity from their redshift and their distance from their brightness. So the redshift, if you don't know what that is akin to a Doppler shift, right? A Doppler shift is the thing that makes the pitch of a train's whistle change as it goes past you, changes the wavelength of light depending on whether an object is moving towards you or away from you. The redshift it's similar to that, very similar, not quite the same, actually, but enables us to make a measurement, let's call it of the velocity of a distant galaxy. But then how to measure the distance? Measuring distances is actually not easy when you don't know the intrinsic brightness or the intrinsic size of the thing you're looking at. But a certain kind of supernova gave us a way around that. So-called type 1a supernovas all have the same, well, let's say similar intrinsic brightness. We know how bright they are were we to be nearby to them. But if they're billions of light years away, we can look at how bright they appear and infer a distance. So that's what was done in the late 90s, actually by two competing groups reporting their results almost at the same time. And this is the summary plot from those two teams. The color is the two teams. It's a plot of the redshift. So here's redshift. So this is redshift of 1. That's nearly 10 billion light years away, if I remember right. And then on this axis is kind of a funny unit, but I'll call it the logarithm of the distance. So this is things getting much further away. And, well, it's hard to see what's going on here, so let's compare these points to the different lines, to this line in particular, which is one of the possibilities that I just mentioned, and that's actually a density too low, the density too low case. So here on the bottom is the data, so the points minus our picture, our model of how the universe expands. And you can see that the points they certainly lie above this line, which is the density being just right, and they actually lie above this line, the straight line, which is the density too low, and they're consistent with something else entirely. And the something else entirely turns out to be a universe that has a density that's just right, in some sense, but a composition that isn't all matter. A composition that is 30% matter and 70% something else. And that combination gives you a different history for how the universe has expanded, and in turn, that history controls how bright, or in this case, how dim, these distant supernovae appear. And that is the discovery of dark energy. So the Nobel Prize in 2011 was given to these three gentlemen for this discovery. And really what that means is, if we step back, so by looking at how the universe expanded, we're able to determine that we don't understand what the universe is made of. We know how much stuff, how much matter and energy is in the universe. Partly, well, combining these measurements with other measurements of the cosmic microwave background. That's the glow from the Big Bang. We know how much stuff is in the universe, but 70% of it is something, we'll call it dark energy, to give it a name. It's the thing that's making the universe's expansion accelerate, making these objects appear dimmer just by a little than they would be otherwise. But we don't know what it is. And that is the challenge for the future. It's one of the biggest pieces of scientific discovery that LSST aims to make, to discover what dark energy is and try to understand that part of the universe better. Now actually, along the way, or as part and parcel of this, we've also found out that we know how much matter is in the universe. The universe is 30% matter, but if you look at how much of the universe is made up of atoms, right? Regular matter that we know and love, the things that are in the periodic table, that only makes up a portion of it. That's 5% of the total. So 25% of the total is some other kind of matter, dark matter. And I should say that if you just pay attention to the names, you can be confused easily, right? They both have dark in their name, right? There's dark matter, there's dark energy. There's no evidence that they're related. That would be awfully interesting, and if they were. But certainly now we have no evidence that they're related. The only commonality between them is that they don't shine. Neither of them emits light or interacts that much with regular matter, if at all. And so they're dark in that sense. And it's also true they're also dark in the sense that they're unknown. We don't really understand either. Okay, so in this talk, we're really going to focus on dark energy. Dark matter will play its role, as you'll see, but mostly we're interested in dark energy. So we could ask, what do we know? What positive things do we know about dark energy? We know a few things. One I already said. It's certainly not regular matter, and it's not regular energy. Regular energy would be heat energy or photons, light energy. It's not that. The other thing we know is how much there is in the universe. We actually know that reasonably accurately at this point. So if we look at the energy density, so that's the energy equivalent in a certain volume of the universe, we find that there is 3.7 proton masses, so you can convert the mass into energy if you like, in a cubic meter. So cubic meter, something like this, 3.7 proton masses, not much. So it's extremely diffuse. What else do we know? Well, the next two are really interesting, okay, because they indicate how strange dark energy is. The energy density stays constant as the universe expands. So regular matter, if you have some volume, it could be a cubic meter, it could be a cubic light year, doesn't matter which. You've got a certain amount of matter encased there. As the universe expands, that volume grows, but the amount of matter doesn't change, so the density goes down. Dark energy does not work that way. As the universe expands, the energy density stays constant, growing with the volume. So as the volume increases, the energy increases such that the density stays constant. So it's an energy that's really associated in some deep way with space. So that's also not the normal way that matter behaves, not the normal way that energy behaves. Lastly, if we look at its pressure, now pressure here is kind of an abstraction because it doesn't interact with regular matter. So it's not the kind of pressure you have in a bottle of nitrogen gas where the air molecules are bouncing off the sides and that gives you the pressure, right? There's no bouncing. But you can think about pressure as being associated with dark energy as a fluid, some sort of abstract fluid. But here too it's odd because the pressure is negative. And the closest analogy you can come to that is a rubber band, right? Where as you pull more in the rubber band, the restoring force grows. And in that sense, it's got a negative pressure. The analogy is not the greatest, frankly. And really, I think there's really no solid analogy for its behavior. Okay, so again, it acts fundamentally differently than the kinds of things we understand well around us, the kind of things we expect from regular energy, regular matter. Now, what can we learn about it? What can we determine about dark energy? Actually, here too is only a few limited things. We can determine how much there is in the universe. We can measure the pressure compared to the energy density, and we can try to look at how the pressure's changed over cosmic times. Is the pressure the same today as it was a billion years ago or 3 billion years ago? Those are the things we can measure. We assume, as a sidelight, I will say, we assume that it's uniform in the universe. And maybe that's a fourth thing we can measure. We can test that assumption. Now, it turns out that this pressure, the actual details of the negative pressure, determine the fate of the universe. So what's going to happen to our universe 10 or 20 or 50 billion years into the future? It's kind of given by this graph. Here's time. 0 is today. This is some distance, where 1 means, it can mean the distance to some distant galaxy. Pick your galaxy, call that distance today 1. Okay, just normalize it to 1. If you go back into the distant past, the distance goes to 0. That's the Big Bang. What happens into the future? Well, here are the two cases I said are not correct. Dark energy tells us it's probably one of these, but the amount of pressure, this ratio pressure over energy density, tells us what happens into the future. And the most interesting case is if W is smaller than -1. In this case, the future may be that space-time itself will be ripped apart. So it's not just, the future, if it were -1 exactly, is also kind of grim. Eventually, you would not be able to observe other galaxies. The other galaxies would have moved, would have accelerated so far away that you could no longer see them. Eventually, perhaps the galaxy itself would be pulled apart. But if this quantity is less than -1, actually space-time itself is doomed. A long time into the future, okay? The sun is gone by then. The solar system is not the same place. But that's actually that's the conclusion we would draw. So in some sense, with LSST today, we are trying to learn about what's going to happen tens of billions of years into the future. Now, what could dark energy be? Let's go one level deeper. What is it? There are a few possibilities that people think about. One is it's Einstein's cosmological constant. I won't go into that history today, but it's a very interesting history if you're interested in the history of science and the history of ideas. That's one possibility. Another is that it's a quantum field, actually in certain ways similar to the Higgs field that gives particle masses that's associated with the Higgs boson. Field could be a little bit like that. If it were, though, there are serious conceptual problems because the amount of dark energy in the universe seems, phenomenally smaller than you might have expected otherwise, were dark energy to be a quantum field. The last possibility is it's a modification of the laws of general relativity of themselves. And that, of course, would be fantastic. So we're trying to learn if we can figure out whether dark energy is one of these things or perhaps something else entirely. Now, how are we going to go about learning more about dark energy? And maybe you can see it because dark energy, it doesn't interact with any normal matter. It's very diffuse in the universe. So we cannot detect it directly. By its very nature, it's indirect. So the first step in our study of it is to look at how matter is distributed in the universe. So this is a simulation. You can see it in 3D upstairs in the Kaipak Viz Lab, along with other interesting simulations of this sort. It's a simulation of actually dark matter. So the lumps here, the bright spots, are hunks of dark matter. And as you can see, as time goes on, it's being pulled together. And this little piece of the universe is becoming clumpier, if you will, as the gravity from the largest collections of dark matter pull in more and more matter. Let's watch it again. So you start out with actually a fairly uniform universe, and as time goes on, you start to develop clumps and filaments. And then as time continues, these come together further, and the universe becomes yet more inhomogeneous. And so what we think is that for many of these bright spots, which are really hunks of dark matter, these are places where galaxies would form. And the key is that how this happens in the universe depends on how the universe has expanded. Very simply, if the universe has expanded more rapidly, then the gravitational interaction, all right, we'll watch it one more time while I'm talking, then the gravitational interaction between matter has less of a chance to operate because the universe is expanding faster. So the universe ends up less clumpy. Alternatively, if the universe expands more slowly, different lumps of dark matter will be closer to each other, will stay in the vicinity longer, the force of gravity will have more of a chance to interact, and the universe will become clumpier. And so it turns out that by measuring how matter is distributed in the universe, is it clumpier or less clumpy, we can tell how the universe expanded. And this is a very, very powerful tool to understand both the expansion and to understand the details of dark energy. And we can do this study at different periods in cosmic time as we look deep into the past. And how do we look deep into the past? Well, we need a telescope like LSST that has capabilities to see very deeply into the universe. A little bit more along those lines. So how do you tell how matter is distributed in the universe? The problem is most of the matter is dark matter. It's not in stars. It's not in galaxies. It does not shine. So how can you tell how much there is and how it's distributed in the universe? Well, you use the only method you have, which is the force of gravity, because dark matter still feels the force of gravity. So you need some way of seeing gravitational interactions. And that is, that we can do directly by something called gravitational lensing. And that's the bending of light by matter. And this is a terrific example here. This is a picture. This is a Hubble Space Telescope picture of a very large galaxy cluster. So that's a collection of, in this case, 1,000 galaxies that have been pulled together by their mutual gravitational interaction into some fairly small volume. Well, fairly small. A million or several million light years on a side. But okay, in this context, that's small. And one thing you notice is that there are these fantastic streaks all over this image. What are those? Those are more distant galaxies than this galaxy cluster. Each of these things you see here is actually a galaxy. Almost everything you see here is a galaxy. But these are other galaxies that are behind, that are further away than this galaxy cluster, and their light is being bent. And it's being bent into these arcs. And so by studying phenomena like this, you can detect matter and how lumpy matter is in the universe without seeing it directly. And in fact, what we'll do is we'll study effects like this. This is called strong lensing, strong gravitational lensing. We'll also go far out from the center of this galaxy cluster, and we'll look at galaxies on the outside. And those won't be bent into these fantastic arcs. Those will just be distorted a little bit. Their shapes will change a little bit, kind of like this, but in a much more subtle way. The importance of that is that these sort of galaxy clusters are relatively rare. Well, LSST will see, a couple 100,000 of them, but relatively speaking, they are rare. And we want to look at the distribution of matter everywhere, across the entire wide field of the sky that LSST will look at. And in that case, the effects are more subtle. Matter is not uniform, it's distributed in lumps, but not so dramatically as this. And likewise, the effect of gravitational lensing won't be as dramatic as this either. But we still need to detect it. So then we come back to this image, which is of, a somewhat more typical region of the universe. And so the thing to point out is almost everything you see here is a galaxy. Or most of what you see is a galaxy. Only a few stars. These are stars. All of these big fuzzballs you see are galaxies. And then of the little ones, perhaps some are stars and some are galaxies. It's hard to tell. Here's one of the challenges we face then, because we need to find many galaxies to study how the light from those distant galaxies to us has been bent by gravitational forces, by gravity, so that we can measure how lumpy matter is, how matter is distributed in the universe, so we can see how the universe is expanded. Did it expand a little faster or a little slower, so that we can learn about, we learn about the expansion, then we can learn about dark energy and dark matter in the universe. Well, to do all that, we need to get a sample of galaxies. I'll talk in a little bit about how big that sample is, but maybe it's worth just showing you what a typical galaxy that LSST will detect will look like. Can you see it in the back? That's this little fuzzball. And then to study those, you want to have stars. Stars are great as a calibration source because stars are in our own galaxy, by and large, these stars are, but they're so far away that they should appear as a point source to us? Well, they don't for various reasons. They appear as a little blob. That would be a typical star. So we have to understand those typical stars to help us understand the typical galaxies to do the science we want to do. But it's worth mentioning that they're not the spectacular spiral-armed things that you see in pictures. Well, a few are. I mean, some of these look pretty impressive. This is a elliptical galaxy, so it doesn't have spiral arms, but some of these are, could be more spiral. And these are pretty far away, so they don't appear that large. But many of them will appear a little bit more like this. They're so far away, they're really just a tiny fuzzball. Okay? So, actually, maybe I'll come back. I'm going to come back to this slide. So, that's an introduction to some of the dark energy science we want to do. We want to understand how matter is arranged in the universe, and to do it, we can measure galaxies. So it's very indirect. You cannot measure dark energy directly. Now, let me change directions just a little and talk about the instrument. Talk about LSST as a project. But before doing that, maybe it's worth defining one word, which you may or may not have been familiar with before: synoptic. If you look it up in the dictionary, well, and you combine a couple of the definitions that you might find, you could arrive at this definition: furnishing a general view over a large area at a point in time. That's pretty close to what we're going to do, with the addendum that we're going to do it at many points in time. Okay, but that defines us. Now, what is LSST? LSST actually is, there are three major legs to LSST. One is the telescope, the observatory facility, all the infrastructure that will be on our mountaintop in Chile. Here's a picture of the primary mirror being constructed. That's one component. That's funded by the National Science Foundation. Another big component is the one we're most concerned with here at SLAC. That's the camera. This is the project that SLAC is the leader of. And I'll talk a little bit more about it, but there are quite a few of us working to start building this beast, and we're very excited about it. The third big leg of LSST is the data management. And that's the group of people that are going to write all the software algorithms to corral the fantastic data set that we'll have. And of course, there's going to be a lot of computing hardware to do all that work as well. Actually, that is a distributed effort, and one aspect of the data handling is here at SLAC too. So there's our group developing exascale-sized databases is here at SLAC as part of the overall data management. Okay, so some superlatives. So it's really how wide, how fast, how deep is LSST? That mirror I showed you is almost 8.5 meters diameter. That's not the largest telescope mirror in the world right now. The biggest maybe is 11 meters equivalent. But it's pretty close, and it's certainly enormous. It's coupled, though, with a system that has a 10 square degree field of view. So that's 3.5 degrees across. The moon is half a degree across. So this is much bigger than the full moon. There are some small telescopes that have a giant field of view like this, but it's the combination that's actually totally unique. The big telescopes have tiny fields of view. Telescopes with big fields of view are pretty small, but we have the combination. And that's the thing that enables us to see so much of the sky so fast and to look so far away. Now, the camera that you need to do that is also enormous. It's the input camera lens. So we go back here. The first thing that the camera has is actually a pair of giant lenses. Is 1.6 meters across. That is pretty close. It's the same size as the biggest refractive telescope ever built. Actually, it's somewhat bigger. And it's I don't know that it's the biggest lens ever built, but I have a feeling that bigger lenses may be kind of on the secret side of what happens in our country or others. It's certainly quite large. The next superlative is the camera. The camera has an array of CCDs, charge-coupled devices, that is 3.2 gigapixels. So now, when this was being designed about a decade ago, or designed really in detail a decade ago, that seemed totally enormous, 3.2 gigapixels. Actually, today, when you can buy a phone with a 40 megapixel camera, it doesn't seem quite as large. But what's really impressive is the size of it. To get good quality images, you can't do it with a small device. It has to be a large device. And so the focal plane is about 64 centimeters across. And so the total area of the CCDs is really enormous. By far the biggest area camera of any astronomical camera. And if you compare it to what's in your iPhone, say, in size at least, the sensor size is about 20,000 iPhones equivalent. So it's fairly large that way. And then the last thing that's impressive is actually it's read out extremely quickly. So only 2 seconds to read out all 3.2 gigapixels. Doing that with the low noise requirements that we have and the other conditions that we're under, that's extremely fast. And so the electronics have to be equal to that task. More superlatives. Well, I said this before. We see the entire sky in 3 or 4 days. That's 15 to 20 terabytes a night. And we'll take images nearly every night for 10 years. And we'll see every spot in the southern sky around, maybe not quite 1,000, but very close to 1,000 times. So it's a way of looking at the sky that's different than any other telescope has really used before. And I'll talk more about that closer to the end of the talk. Some final superlatives. We'll observe 20 billion galaxies. That's an appreciable fraction of the total number of galaxies that we would ever conceivably be able to observe based on the age of the universe and the speed of light. We'll also see 17 billion stars, so those are stars in our own galaxy. We'll see objects in our own solar system, 6 million solar system objects, and every night we'll get 10 million alerts. The computing system will spit out a message that says something has changed in the sky. And I'll come back to this one a little bit more. And the last thing that's really actually I think is going to be fantastic is that all of our data is public. Okay? So public to the entire scientific community, at least in the US, France and Chile, and perhaps in the whole world, but it will be public not just to scientists, but also to interested citizens, citizen scientists. And that has not been done in any way like this before either. All right, I'll show some pictures. So LSST is going to be on a mountaintop called Cerro Pachón. It's in the Chilean mountains. These are engineering drawings of what the observatory and the dome, you can see the telescope inside the dome, will look like. This is a picture I took myself a couple of years ago. At that point, the mountaintop had been cleared, but no more construction had been done. And this is a picture taken more recently, showing sort of the start of construction. So at least there are trucks. There are trucks and workers there. Things are getting going. The camera. Let me just say a little bit more about the camera. So this is the piece we're doing here at SLAC. I know some of the engineers working on the camera are here. Steve Kahn here has been the leader of the camera project for 10 years, perhaps, and now he's also the leader of the entire observatory as well. So here's the camera that we're going to build. Well, you call it a camera, but this is 1.6 meters across. It's almost 4 meters long. So it's kind of as large a thing as you could ever call a camera. But it has lenses. There are 3 lenses. It has a shutter. One of these things here is actually a shutter that will close and open to let light in or not. There's a filter exchanger. So we have giant filters that admit only one sort of narrow band of light at a time. And we have 6 filters total. We can only fit 5 of them in here. When they're not in use, we actually slide them off to the side, kind of along the side, so they don't stick out outside of this cylinder. And there's actually quite an impressive mechanical device to get them from here to here reliably. The green is the cryostat. So that's the vacuum vessel used to keep the CCDs cold. And then in the front of that, you can kind of see it drawn schematically. These squares are the CCDs, 189 CCDs. And then in the back, there's equipment to cool the cryostat. There's refrigeration equipment, as well as electronics and other control equipment. And then this entire camera assembly bolts on to the right spot in the observatory, kind of at this plate back here. So we are just starting construction now. We're still, the design phase is mostly over, not entirely over, but mostly over, and we're really seeing into actual construction. So just a few pictures. And I should say, you know, SLAC is where most of the activity is, but as these things work, we have a collaboration, including Livermore, Brookhaven, a couple laboratories in France, and a couple other universities in the US to help us build this camera. So the center picture is IR2, so if you've never been over there, that's where the Babar experiment ran. Now that Babar has been removed, we're making use of part of that space, sharing it with the LZ dark matter experiment, to build this giant clean room. And we'll do the camera assembly and testing in that clean room. So here you can see it taking shape. Here are some CCDs, some sort of first article type CCDs on a plate. So each plate holds 9 CCDs. Here are 3. Here is the crate, we call it, that holds the electronics for the CCDs. And one of the several innovative things we're doing is that there's so many channels for this camera that instead of taking out analog signals out of the cryostat, we're digitizing inside the cryostat. And that really, there's maybe one other camera that's done that, but by and large that has not been the practice. So here's the electronics board, prototype of the electronics board that will read out the camera. Here's other work going on at SLAC. This is the refrigeration test bed. This is testing the somewhat novel Joule-Thomson style refrigeration unit that we're going to use to cool the camera. Refrigeration is easier if your object stays still, but since it's a telescope and you're moving across the sky, and actually we're moving across the sky quite rapidly, that places a whole set of interesting demands on your refrigerator. And this is just an engineering drawing still. We have a contract now for the 2 giant lenses, and so those will be made by Ball Aerospace. So things are happening. So with the remaining time, actually, I want to come to my third topic. So we talked about dark energy. We talked about how to make measurements of dark energy. We talked about the capabilities of the instrument and how those are matched to studying dark energy because we're so deep, because we're able to see objects, galaxies so far away. But there's a whole other aspect, there are many other aspects to the science we'll do with LSST besides dark energy. And I'll just talk about one of them in general today, and that's the alerts, the ability to see changes in the sky. And this is enabled by the fact that we look at the same part of the sky many, many times. This is the fast part of the LSST mantra. And so an alert is any object observed to change in the sky. And, well, I said already, we'll get 10 million per night. And those will be detected and transmitted. The promise is within a single minute of their observation. So really real time. As images are being taken, the data is sent to processing farms, and it's analyzed really instantly to look for anything that's changed in the sky. What would those changes be? Well, one are new objects, things that just didn't exist before. Supernova are a great example. So we'll detect literally thousands and thousands of different kinds of supernova. Another thing are objects that are there, but they change. Variable stars are a good example. There's no lack of variable stars in our own galaxy or in nearby galaxies that are interesting to study. We'll also look at objects that move in the sky. things in our own solar system, by and large. Kuiper belt objects. So the Kuiper belt is, those are objects past the orbit of Neptune that are interesting to study, and as well as asteroids. So we will look for killer asteroids. And lastly is the thing that I can't list because it's the unexpected. And I think here, so in addition to making discoveries about what dark energy is, my personal feeling is that this is the place where LSST is really poised to discover something new, because we're looking at the sky in a much different way than it has been before, repeatedly, to great depth. If we're looking at distant or just very dim objects. Depth can be both distant objects or dim objects that are nearby, and we'll be doing it over and over. And so I am quite confident that we will discover new things along these lines. Now, there are challenges. Well, one, there are opportunities. The data is public. Anyone could look at this stream, this fantastic stream of alerts, and look for something new in it, or study phenomena that they already know about and are interested in. But it really does present a challenge, because how can you follow 10 million alerts per night in any kind of reasonable way? That is a phenomenal challenge. Let me talk a little bit in the remaining time about the alerts, about changing objects in the sky. So one thing, just to make it a little more concrete, how LSST observes, one of our colleagues made this kind of simulated view. So again, this is the whole sky, north, south, one end of the celestial globe to the other. This line is the night sky. So this is what's visible at night from Chile. This is where you point straight up. Here's the moon. Here's where the planets go. And then this is the galaxy over here. And so each one of these little hexagons is one LSST image. And this is a simulation of how you would observe over time. So this is night, well, start from 0. So this is the first night. And you can see we're tiling the sky kind of back and forth. The colors actually mean something. It's purple is one of the filters, the so-called Y band, and that was used because the moon is up. Here's the next night. We're observing in a different filter, and then we stay for a while at this spot. And we haven't given up then. There are actually certain spots on the sky that we look at even more frequently than every 4 nights. And those are special places where we look where we really want to see supernova, but we might see other interesting phenomena as well. And so here's the third night, and you can see at this point we have really tiled quite a bit of the available sky. And this will actually all be done under computer control. There's no way you could have someone sitting figuring out where to take the next image every 15 seconds. You can't do that for an hour, much less for multiple nights. So yeah, here's the night 3, so it's the 4th night. And now you can see we've tiled just about the whole available sky in that period, and we've done it in different filter bands, and some we've seen twice, and maybe there's some regions we haven't quite seen once. But it averages out to seeing the whole available sky every 3 or 4 nights. Well, and this continues for a long time. We won't continue to watch it, but that's what we'll be capable of doing. So what will we see then when we look at the sky repeatedly? Here's one example. This is an example from another project I'm working on, the Dark Energy Survey. Dark Energy Survey is kind of a junior version of LSST, maybe between 50 and 100 times less capable. Pretty interesting right now, much bigger than anything that's happened to date. And we certainly hope to learn, we will learn a lot that will inform LSST. Here's a supernova. Here's the before. You can see there's a fuzzball there. But after, it's actually a bigger fuzzball. And if you take the difference of these two, being very careful to take into account the different conditions. The sky had a different brightness, the images had a different quality. Observing on Earth is not so easy. Things are not that static. But if you do things right, you see the difference, you get this little dot. And that is a supernova. And it's actually not a normal supernova. It's a superluminous supernova that doesn't decay away very fast. And actually, people are confused about exactly what those objects are. All right? And I think that, here's an example. We've detected lots of supernovas, but LSST is going to see so many, I would be surprised if we don't find different sorts of supernova from LSST. Here's another type of object. So here are solar system objects. These are Kuiper belt objects. And so if you look at, I think these are two different ones, but this little dot you can see is moving across the sky. The stars are sort of set up to be fixed in the image, but you can see the moving object. This is how the planets, well, I was about to say Pluto. It's not a planet anymore, but it was discovered this way with photographic plates. Using our fantastic camera, we'll see, remarkable numbers of these. Another way to see, another way that Kuiper belt objects will appear, shown by this kind of visualization put together by my colleague Dave Gerdes from data from the Dark Energy Survey. These regions are the Dark Energy Survey focal plane, their CCD set. And the dots are where Kuiper belt objects appear. And the color scale here is over time, from 2012 to 2014. And these orbits are the apparent orbits of the Kuiper belt objects. Now, mostly what you're seeing actually is the Earth's rotation. These things are so far away, they take hundreds and hundreds of years to go around the sun. So in 1 or 2 years, they don't move very far, really, but they do move a little. But mostly they appear to move because we're moving. We're going around the sun, and our vantage of them changes. But you can use that to your advantage to find them, to link together different images taken, and prove to yourself that that's the same object from one image to the next. And they trace out these interesting orbits. Dave has found a handful in this region of the Dark Energy Survey. They'll find plenty more. LSST will find a spectacular number. And so the 6 million number I mentioned of solar system objects is, some good fraction of that will be these Kuiper belt objects. So people studying the solar system will really go to town. One last thing in alerts. These are the things we know about. Asteroids, or in particular, killer asteroids. So this is a plot of, this is diameter. This is the number of objects. The red is sort of an estimate of what's been discovered as a function of size. So we think, and the blue is different models of how many asteroids there are in near-Earth orbits. So we think we found all of them that are bigger than a kilometer that could ever hit us. So those are the ones which, really cause damage. Here's the size of the asteroid that, I guess, made the dinosaurs go extinct. Here's the Russian asteroid that hit in the early 20th century. I am told that our government has a law or a demand that some projects find all asteroids bigger than 140 meters diameter. So that's around here. And that's an interesting point because at that size, they don't burn up in the atmosphere. And if they hit the ocean, they'll cause a tsunami. And they could cause a pretty damaging tsunami. So it's a level at which you really have to worry. Here, well, they could do some damage. It's of a different character. But here, there are real problems. And the red curve is how many we've discovered, and the blue is how many we think there might be. And you can see that depending on where this is, we've only found 1 in 10,000, 1 in 1,000 or 1 in 10,000. So there are lots and lots of them. And LSST, we think, will find about 90% of those. So it will find, not all, but almost all. And, well, that'll be interesting to study as well. Although you may find, more frequent messages in the news media about some object that may or may not hit the Earth. So, but at least it's better to know than not know. Okay, so one last comment. And it's really related to the fact that the data will be public and all these alerts will be public. And so science recently has taken on different efforts to get science into the public's hands more directly. Not just telling people about what we're doing, but finding ways for them to do it too. Citizen science. one of the most interesting, one of the originators really of this is the so-called Galaxy Zoo. And actually any of these you can just go online and look up if you're interested. Galaxy Zoo, which supplied little pictures of galaxies found in the Sloan Sky Survey to the public and said, try to classify these galaxies for us. Use your eyeballs and your brain, which are still much more powerful than computer algorithms for certain kinds of problems. Why don't you use those for us and classify what these galaxies look like? Another case is space warps, developed by Phil Marshall here at KIPAC, to look for gravitational lensing. These little arcs are similar to the arcs in the galaxy cluster I showed earlier, and those are not easy to detect in objects like this, but your eyes, your brain, are still quite good at doing it. LSST may have so many of these that, putting these before the public and harnessing the power of thousands of people to look at them may be maybe a good way to go, maybe the only way to go. And then last, the LSST project has an iPhone app called Transient Events, which will supply events to you from a smaller survey that's going on now. It's the Catalina Sky Survey. But when LSST starts, this kind of product will produce this fantastic flow, 10 million events a night. And I think there's a lot of potential for us and for our partners in the community to do more. Some final thoughts. So we have a schedule, as any kind of project like LSST does. We have a schedule. That schedule shows us delivering the camera to Chile in 2020. I can't wait for that. At the observatory, I think the first light, the first time we put the full camera and take an image of the sky, I think will be later that year, in 2020. There's some time to tune things up, to commission the entire facility, but our 10-year survey will start in 2022. I talked about dark energy, I talked about transients or alerts. There's much more science that you'll be able to do, that people will be able to do with LSST, and discoveries await. So with that, I thank you. Well, I'd be happy to entertain questions. Greg has one in the front.
I have two questions. The first one is probably a nitpicking question, but I didn't understand how this would work. You said that, by pointing to this podium here, that in the universe, on average, there were 3.7 protons per cubic meter.
Proton equivalents. The equivalent energy, so in dark energy, if you want to sum up how much energy is there, it's the energy that, whatever that number is, 3.7 protons have.
Okay, so
but
when
the energy equivalent, not protons themselves.
No, but then if the universe grows, then for the energy to stay constant, the energy must be increasing.
Yes.
Okay, good. The second thing is you gave a phenomenal description of this instrument, but can you just remind us again, you're going to discover a zoo, a mega zoo, okay? But how does that discovery of the mega zoo resolve the question of what dark energy is, unless you have some kind of model?
So it's really the indirect sequence of steps I mentioned, right? We'll observe billions of galaxies. Not all of them will be usable for gravitational lensing, of the 20 billion, but maybe 4 or 5 billion will be usable. So we'll study those 4 or 5 billion galaxies, and in particular, we'll measure their shape, we'll measure their brightness, we'll measure a crude version of their redshift from the different filters we have. And from those things, we'll then infer how matter, and it's mostly dark matter, is distributed around the universe. I mean, the technical thing we'll do is we'll measure the power spectrum of dark matter. So that means, how is the matter distributed? Is it smoother or is it clumpier in space? And that will tell us how the universe expanded, and that will tell us about dark energy. It's really this whole line of inferences that you need to do it, because there's just no way to see it directly.